In the last lecture, we had briefly summarized the characteristic length for diffusion for the case where the Peclet number is large, so that convection is dominant compared to diffusion. And in that case, the mass or energy that is being diffusing out from the surface is rapidly swept downstream, and therefore, the variation in the temperature or the concentration due to the surface boundary condition at the surface is restricted to a thin region close to the surface, whose thickness is much smaller than the characteristic dimension of the object. And we had looked at that for different cases. This characteristic length depends upon the Reynolds number and it depends upon the boundary conditions at the surface. For low Reynolds number, we had seen that for no slip condition it is P e power minus 1/3 times the dimension. For a slip boundary condition it is P e power minus half, the Peclet number power minus half, all in the limit of high Peclet number or strong convection. For a laminar flow in the high Reynolds number limit for the flow past a particle, you get R e power minus 1/6 times P e power minus 1/3 or R e power minus half times the Prandtl number power minus 1/3. In the case of mass transfer, you substitute the Schmidt number for the Prandtl number. Okay. For a pipe flow, it is P e power minus 1/3 times d by L power minus 1/3. Okay. And for the flow in a thin film, you get P e power minus half times h by L power minus half. Okay. And so long as this characteristic distance is much smaller than the thickness, you can assume that the system the steady state correlations can be used in order to calculate even time varying properties or spatially varying properties. The diffusion time in all cases will scale as the diffusion length square divided by the diffusion coefficient, d for mass transfer, alpha for energy transfer. Okay. So, that is the diffusion time. So, that so long as this diffusion time is much smaller than the time for evolution, you can use the steady state approximation, and so long as this diffusion length is much smaller than the dimension of the object, you can locally use a correlation derived assuming that the temperature difference is a constant or the concentration difference is a constant. Okay. You can use a correlation derived in that way. And we are looking at an example. Okay. In this case, the diameter of the object was 1 centimeter, okay, of a steel sphere, and we were asking the question, if the initial temperature is 300 degrees centigrade and I want to cool this sphere and I blow air past it, air at 0 degree centigrade is blown past the sphere, how long does it take for the temperature to reduce to 100 degrees centigrade? That was the problem. First thing, we have to see whether this is in the low Peclet number or the high Peclet number regime. Okay. Pe, you recall, the Peclet number is equal to the free stream velocity times the diameter by alpha. Okay. In this case, it is the thermal diffusivity of air. Okay. The thermal diffusivity of air in turn is equal to K air by rho air times Cp air, okay, which is equal to the thermal conductivity of air is 2.4 into 10 power minus 2 watts per meter per degree centigrade divided by rho air, which is 1.25 kg per meter cubed into, okay, the specific heat of air is 10 power 3 joules per kg, okay, per degree centigrade. And as you know, this in the end has to have dimensions of length square per time because it is a diffusivity. If you do this calculation, you will get 1.9 into 10 power minus 5 meter square per second. That is the thermal diffusivity, and as expected for a gas, this is of the order of 10 power minus 5 meter square per second. Okay. For gases, I told you that the thermal diffusivity is usually of the order of 10 power minus 5 meter square per second. So, the Peckley number is 1 meter per second into 0.01 meter. 1 centimeter was the diameter of the object, okay, which was 0.01 meters, okay, and divided by 1.9 into 10 power minus 5 meter square per second, which turns out to be equal to 520.8. Okay. That is the dimensionless Peckley number. Okay. So, the Peckley number is actually large in this case, and the thickness of the boundary layer is 1/3 power of this. The ratio of the thickness of the boundary layer and the diameter of the sphere is the 1/3 power of this. Okay. So, now that we know that it is in the high Peckley number limit, we have to use the Nusselt number correlation for high Peckley number, which we had stated earlier, okay, and which we will derive later, 0.992 times P per 1/3. Okay, that is the Nusselt number correlation. Okay. Now, the time for evolution of this sphere, okay, we get that from an energy balance. Okay. The change in rate of change of energy, okay, the rate of change of energy of the sphere, the rate of change of the thermal energy of the sphere is going to be equal to the mass times Cp. Okay. Is equal to mCp into dt by, okay. This Cp is the specific heat of steel. Okay. Okay. This is equal to pi by 6 d cubed rho steel times Cp steel times dt by dt. Okay. This has got to be equal to the energy transfer rate out of the sphere, which is the flux times the surface area. Okay. So, I will get pi d cubed by 6 rho s Cps dt by dt is equal to the average flux, okay, times the surface area pi d square with a negative sign, because as heat is conducted out of the sphere, the temperature should decrease. Okay. Okay. And I can write this flux in terms of the Nusselt number correlation. Okay. It's equal to minus k into T minus Tf. Okay. Tf is the temperature of the fluid. In this case, as you recall, it was 0 degrees centigrade. The air was being blown past at 0 degrees centigrade. Okay. Divided by d into the Nusselt number, okay, times pi d square. Recall that the Nusselt number is the ratio of the average flux and k times delta T by d. Okay. So, the average flux I have written as k times delta T divided by d times the Nusselt number. Okay. And you can do some simplification here to get dt by dt, okay, is equal to minus 6, I should be careful here, this is k of air, okay, 6 Ka T minus Tf Nu by rho s Cps d square. Okay. Divided by the characteristic time. Okay. This we have already seen before. Okay. This we have already seen before, where Tc is the characteristic time. Okay. Tc is equal to rho s CPS d square by 6 Ka times the Nusselt number. Okay. And substitute the Peckley number correlation for the Nusselt number. Okay. The Nusselt number correlation in terms of the Peckley number for natural convection in the limit of high Peckley number. Okay. So, we will substitute that in this case. This is rho s CPS d square by 6 Ka into 0.992 PE per 1/3. Okay. So, that is the correlation, and here the density of steel is 8 into 10 power 3 kg per meter cubed. Specific heat is 500 okay, joules per kg per degree centigrade. Okay. Okay. Into d square, which is 0.01 meters the whole square, by 6 into 2.4 into 10 power minus 2 watts per meter per degree centigrade. That is the unit of the thermal conductivity. Okay. Into 0.992 into 520. Okay. 0.8 whole power 1/3. And you can evaluate this. This comes to about 348 seconds. Okay, this comes to about 348 seconds. Okay. So, that is the characteristic time. I can solve this equation. Okay, I can solve this equation in order to get what is the temperature, okay, T minus Tf by Ti minus Tf, where Ti is the initial temperature, is equal to e power minus T by Tc. Okay. This we had already seen before. Okay. This solution we had already seen before. This temperature at a time T minus the fluid temperature divided by the initial temperature minus the fluid temperature, it is an exponential decrease in time. Okay. We need to know what is the time for which the temperature decreases to 100 degrees centigrade. If the fluid temperature is 0 and the temperature of the initial temperature is 300. Okay. So, 300 minus 0 by, I am sorry, this should be 100. The final temperature is 100 by 300 0 is equal to e power minus T by 348 seconds. Okay. Just substituting the initial temperature, the final temperature, the fluid temperature, and the characteristic time. Okay. And from this you will find that T is equal to 382 seconds. Okay. So, that is the amount of time it takes for the temperature of the steel sphere to decrease to its final value. Okay. So, this is an example of the time scale. Okay. So, the times the diffusion time in this case, okay, let us look at the diffusion time in this case, will be equal to the diffusion length square by alpha, okay, and the diffusion length I told you at high Peckley number for laminar flow goes as P power minus 1/3 times d the whole square by alpha, okay, which is P power minus 2 by 3 d square by alpha. Okay. And you have to estimate this, okay, P power minus 2/3, 520 power minus 2/3 times d square is 0.01 square, so 10 power minus 4, divided by alpha, which is 1.9 to 10 power minus 5. And you can verify by doing this calculation that this is actually a small number. Let us take another example. Okay. We had looked at dissolution of a sphere in a quiescent fluid in the absence of any flow. Okay. Let us now look at the dissolution of a particle due to natural convection. Okay, let us look at the dissolution of a particle due to natural convection. Okay. So, we take a spherical particle of diameter d, okay, a spherical particle of diameter d, okay. Density rho s, specific heat Cps, okay, in a fluid with okay, characteristic velocity Vc and diffusivity d, okay, and surface concentration at the surface is Cs. Okay, so, surface concentration here okay, and fluid concentration far from the surface is equal to 0. Okay. We had derived this for a camphor particle when the diffusion is due to when the transport is due to diffusion. Okay. In this case, we are considering the limit of high Peclet number where convection is dominant, and we want to know how the diameter of the particle varies with time. Okay. Okay. From some initial diameter d naught. Okay. Okay. If we take an initial diameter d naught, how does the diameter vary with time? The rate of change of mass of the particle has got to be equal to minus the mass flux, average flux, times the surface area of the particle. Okay. That is the balance. Okay. Rate of change of mass is, I will use partials here because I have a variation of diameter with respect to time, though this is actually a total derivative. But I will use a partial derivative here because I have to represent the change of diameter with respect to time. Okay, so, I will use d by dt of pi by 6 d cubed, okay, rho of the solid, okay, is equal to minus JAV into pi d square. Okay. Differentiating by chain rule, you will get that pi d square rho s by 2 partial d by partial t is equal to minus pi d square into the flux. Okay, the flux is expressed in terms of the Sherwood number correlation, d times Cs, d times delta C by d. D is the diffusion coefficient, Cs is the surface concentration. Note that rho s is the density of the solid, okay, rho s is the density of the solid, whereas Cs is the concentration of the solute in the fluid at the interface, okay, into the Sherwood number. Okay. So, the rate of change of diameter is going to be equal to minus 2 d Cs into the Sherwood number divided by rho s into d. Okay. Note that the Sherwood number correlation also contains a diameter in it. Okay. So, therefore, we have to expand out this Sherwood number correlation. You will get minus 2 d Cs into divided by rho s d into the Sherwood number, which is 0.992 Vc d by d whole power 1/3. Okay, so that is a Sherwood number correlation. Okay. So this contains a d power 1/3 in the numerator. Okay, this contains a d power 1/3 in the numerator. Okay. Okay, just cancelling out the powers of d power 1/3, I get a d power 2/3 in the numerator, v power 1/3, and I get a d power 2/3 in the denominator. Okay. So I can multiply both sides by d power 2/3 and I will get d power 2/3 partial d by partial t is equal to minus 1.984 d power 2/3 Cs Vc power 1/3 divided by rho s. Okay. Integrated once with respect to time. Okay, integrated once with respect to time, I will get 3 by 5 into d naught power 5 by 3. The integral of d power 2/3 times partial d by partial t is equal to d power 5/3 divided by 5 by 3. Okay. Where d naught is the initial diameter at time t is equal to 0. Okay. There was a negative sign there on the right side. I have multiplied by minus 1, so that on the right side I get a positive sign. On the left side I have originally had the final diameter to the 5/3 power minus the initial diameter to the 5/3 power, multiplied that by minus 1 to get initial diameter to the 5/3 power minus the final diameter to the 5/3 power. Okay. So this gives you the variation of diameter with respect to time. Okay, this diameter is a function of time. Okay. Or I can multiply throughout by 5/3 and I will get d naught power 5 by 3 minus d power 5 by 3 is equal to about 0.3 d power 2 by 3 Cs Vc power 1/3 times t divided by rho s. Okay. The total dissolution time is the time at which the diameter is equal to 0. Okay. The total dissolution time is the time at which this diameter is equal to 0. Okay. Therefore, the dissolution time is the time at which this diameter is equal to 0, or this is equal to rho s times d naught power 5 by 3. Okay. By 0.3 d power 2/3 Vc power 1/3 times Cs. Okay. So this is the final dissolution time, and you can easily verify that the quantity on the right has dimensions of time, because both rho s and Cs are quantities with dimension of mass density. Okay. Rho s has dimensions of total mass per unit volume and Cs has dimensions of mass of solute per unit volume. Nevertheless, they have the same dimension, so they cancel out. In the denominator, I have d power 2/3 and Vc power 1/3. Okay. That has the dimensions of length power 5/3 divided by time. Okay. So therefore, the dissolution time that I get is going to be equal to this value. It increases proportional to the 5/3 power of the diameter when there is natural convection at high Peclet number. Okay. Recall that when we had forced convection, it was increasing proportional to d square. just from dimensional analysis. It has to be d squared divided by the diffusivity. In this case it is natural convection, it is increasing as the 5/3 power of the diameter. That is because the you have a factor of Peclet number to the 1/3 in the expression for the shower number. Okay. You have a 1/3 power in the Peclet number in the expression for the shower number, and because of that you get a 5/3 power. Okay. So, these are a couple of examples of how you can include correlations in the expressions for the time varying temperature or concentration fields, okay, to calculate, for example, the evolution of temperature or the dissolution of a particle. Okay. This is for natural convection. We had seen, I am sorry, this is for forced convection. Earlier we had seen the situation for natural convection. I am sorry, the yeah. So, what I just solved was for forced convection. Before that we had seen diffusion dominated. Okay. And finally, we will examine the case of natural convection. Okay. Natural convection from an object, okay, in the limit of high Grashof number. Okay. If you recall, Grashof is equal to rho square and the Prandtl number is equal to Cp mu by k. Okay. These are the two independent dimensionless parameter, and the correlation for the Nusselt number is it is equal to some constant which depends upon Prandtl number times Grashof number to the 1/4 power. Okay. In this case also, in the limit of Grashof number much larger than 1. Okay. This correlation applies in the limit of Grashof number much larger than 1. In this case, if the d is the characteristic diameter, okay, of the object, the temperature disturbance is restricted to a thin region around the object in the limit of high Grashof number, where the thickness of this region, okay, the thickness of this region, the diffusion thickness, diffusion length divided by the characteristic dimension is equal to Grashof number power minus 1/4. Okay. That is the thickness of this region for natural convection at high Grashof number. Okay. So, you can apply equations, the correlations of this kind that are derived for steady state, okay, configurations, provided the characteristic time for the formation of this boundary layer is much smaller than the time for evolution of the temperature at the surface, or when the characteristic length of the object is much larger than the thickness of this boundary layer, which will always be satisfied, because in the limit of high Grashof number this characteristic thickness is actually very small compared to 1. If you recall, when we did dimensional analysis, we found that the Grashof number goes as in the range 10 power 4 to 10 power 9 or so, okay, under normal circumstances. And in those cases, the temperature disturbance is always limited to a thin region close to the surface. And in that case, you can assume that the correlations of this kind that are derived for steady configurations with a constant temperature difference between the surface and the bulk are valid, okay, provided the characteristic length is much larger than the diffusion length, or the characteristic time for the evolution of the temperature field is much larger than the diffusion time. We will look at a couple of examples of applications for the evolution of the temperature of an object at high Grashof number for laminar flow. Okay, so, this is always for laminar flow. I told you that the flow becomes turbulent when the Grashof number increases beyond about 10 power 9. Okay. So, if the flow is laminar, then we can use this correlation and use that in balance equations. We will examine that in the next lecture. I will see you then.